In this video, we continue our discussion of model selection. In the last video, and for the past week in class, we talked about how to use various subset selection methods, along with cross-validation, to try to reduce the number of variables in our model and make them more parsimonious. In this video, we will learn a different approach to model selection called Lasso. Cross-validation will once again play a key role in the tuning process. When we fit linear models using ordinary least squares, the estimated coefficients, beta 1 hat through beta p hat, are those that minimize the residual sum of squares, RSS for short. That is, we find the beta 1 through beta p such that the sum of the squared differences between the actual and fitted values is as small as possible. Keep in mind, RSS will decrease as the number of terms in our model increases, even if those terms are random noise, or garbage variables, as I like to call them. The Lasso, which stands for Least Absolute Shrinkage and Selection Operator, minimizes a different quantity than in least squares regression. But notice that the first part is still the residual sum of squares. The second part is what is referred to as a penalty term, and it is the sum of the absolute value of the coefficients times a parameter lambda. These two pieces compete with each other. The RSS piece on the left will be smaller when more terms are in the model, and coefficient estimates fit the data well. The penalty term on the right will be smaller when coefficients are small. It is smallest when the coefficients are all equal to 0. So the penalty term will shrink coefficients, sometimes even shrinking them to 0. The Lambda Tuning parameter allows us to choose how much to penalize the coefficients. We have two extreme cases. When lambda is 0, there is no penalty, and all coefficients are included with regular least squares coefficient estimates. When lambda equals infinity, the coefficients would all need to be 0, and we end up with a model with only an intercept. So, as lambda gets larger, some of the coefficients will shrink to 0. These are typically the weaker predictors. Since some of the coefficients are shrinking to 0, this method is a form of model selection. Only the terms with non-zero coefficients are used in the model. We will use cross-validation to choose the best lambda. And one more important piece before moving on to a couple examples. Because we are penalizing coefficients, it is important that we put our variables on the same scale so that coefficients are being penalized fairly. In the functions we use, they will be automatically scaled to have mean 0 and standard deviation 1. If we didn't do this, variables that are measured on larger scales would be penalized more than those measured on smaller scales. For example, the same variable measured in pounds would be penalized more than if it were measured in ounces. Again, the functions we use will do this part for us. It will also display the final coefficients in the original scale so that the model is interpretable. In this example, I generated 500 y's from the equation shown in the title of the graph in the top right corner. Y equals 10 plus 3x1 plus 0.5x2 yes, plus epsilon, where the errors are normally distributed with mean 0 and variance 25. So x1 is a quantitative variable, and x2 is a categorical variable with levels yes and no. The graph in the upper right shows a plot of the sample of data, and the least squares regression equation is shown on the plot. Next, we use Lasso. The graph in the lower right illustrates the results of Lasso. Specifically, it shows the lambda value on the x-axis versus the estimated coefficients for the two variables on the y-axis. The detail for the lambda values indicated by the black vertical lines is shown in the table on the left. For example, when lambda equals 0.25, the x1 coefficient is 2.88, and the x2 yes coefficient is 1.09. Those are indicated by the blue stars on the graph. Right around lambda equals 1 is where the x2 yes coefficient shrinks to 0. The data used in this example are from the ISLR package that goes with the Introduction to Statistical Learning textbook. There are 400 simulated observations of credit card data. The response variable is balance, which is the average credit card balance in dollars. There are more than 10 explanatory variables, but we focus on income, credit rating, and a student indicator variable. Both graphs on the left are like the graph in the lower right on the previous slide. They show the estimated coefficients from the Lasso for various values of lambda. The one on the bottom is zoomed into a smaller range of values on the y-axis to show the details more clearly, but in doing that, we lose view of the student variable. In general, we see that as lambda increases, more variables have estimated coefficients of 0. How do we choose the best model? We use cross-validation, of course. The graph on the right shows the cross-validated RMSE for various values of lambda. Lines are extended one standard error in each direction from each cross-validated standard error. The pink vertical line indicates the value of lambda with the smallest cross-validated RMSE. We could choose this as our best model. But if we really want a simple model, and we know that there is some variation in the RMSE, it could also be a good idea to choose a simpler model with an RMSE that's still close to the smallest RMSE. What is close? It is recommended to choose the largest value of lambda, such that its cross-validated RMSE is still within one standard error of the smallest cross-validated RMSE. The turquoise vertical line indicates that lambda. The pink and turquoise lines are also represented in the graph on the left, so you can get a sense of the difference between those models. In the graph on the right, the red horizontal line is the value of the smallest cross-validated RMSE plus one standard error. So we are looking for the largest lambda whose RMSE is below that red line. A larger lambda will give us a simpler model. So, as mentioned before, we often choose this value of lambda rather than the lambda with the smallest RMSE. That's all for this video. In class, we will learn how we can use the functions from the Caret package to help us fit and tune Lasso models.